All right, so today we're going to be comparing ideal and real gases. So obviously everything that we work with in the lab and in the real world is a real gas. And we've talked about the ideal gas law, but we haven't really talked about why we call it the ideal gas law. The ideal gas law is called that because in order to really use the ideal gas law to solve for like a pressure or a volume or something like that for a gas, we have to make some assumptions that come from something called the kinetic molecular theory. So the kinetic molecular theory is just a way of explaining gas behavior that essentially says that a gas is just a volumeless, dimensionless little point in space. Gas particles are made up of these little points in space that bounce around, run into each other, and collide and bounce off the walls of their container. And so if we think about what's happening there and what's wrong with that idea, so if we take like a model here from our little FET activity, and we pump a little bit of, let's just say, the smaller gas into this container, right? What we're imagining here, if we just kind of pause this, is that these little red particles are, let's say, like helium atoms. And those helium atoms are so tiny that their volume is the volume of the entire container. The gas volume, so if we were to solve for V and PV equals nRT, we would be solving for the volume of the entire container. And that's more or less accurate. But in reality, those helium atoms actually take up some space themselves, which is the reason that we can't just scrunch this thing down to zero volume, because eventually we'll run into a point where we've got helium atoms that can't be compressed any further. So that's one thing to keep in mind. The volume of the space that the gases occupy does include the gas particles themselves, even though they're really, really tiny. The other thing to keep in mind is these things bounce around, and you don't really see it with this simulation. They're going to have intermolecular forces. So like even helium atoms would have London dispersion forces. So if you just kind of keep your eye on a couple of atoms as they collide, they're transferring energy, right? But that transfer of energy is perfect in this case, meaning that as one particle comes in and hits another particle, all of the faster one's energy is translated, or all of its excessive energy, I guess I should say, is translated to the other particle. So there's no net loss in energy. Well, if we think about it, if they have London dispersion forces and they sort of have a magnetic attraction for each other, some of that energy is going to get lost because of that attraction, that sticking that happens. And in fact, if we cool these things down enough, and again, you won't be able to see it with this simulation, but if we cool these things down enough and really slow them down, they could even condense into a liquid or freeze into a solid. So we already know that real gases don't have quite the pressure we expect. And that's because, again, as they collide, they're not having these perfectly elastic collisions where they bounce away, having conserved all of their energy. The intermolecular forces cause some of the loss of the elasticity in that collision, some of the loss of energy. Okay, so the kinetic molecular theory ignores two things. It ignores the intermolecular forces, and it ignores the actual volume of the particles themselves, which they do have volume even though it's really, really small. Okay, so if we were at higher pressure, would we expect a real gas to deviate more or less than at low pressure? Okay, so hopefully if we're thinking higher pressure means more collisions, and more collisions, that means more opportunities for these things to stick together and deviate more. Okay, so higher pressure means more collisions. More collisions is more opportunity for those real gases to interact with each other, to stick together, to attract each other because of their IMFs, compared to at lower pressures. So lower pressure would just mean fewer collisions, less opportunities for them to attract each other. So go ahead and pause and think about your why here. I'm not going to put it up on the screen for you, but I did just explain it. So think about your why, and if you need to re-listen to the last couple seconds of the video, then do that. But why is it that at higher pressure, real gases deviate more than they from the ideal gas model than they would at lower pressure? Okay, and then what about temperature? So at lower temperature, so as I take these particles and cool them down, right? So let's cool them down even more, even more, even more. So that's going to, now let's assume that we're keeping the pressure the same. So maybe I have to put in a little bit more gas to keep the pressure the same. But generally speaking, the slower they are moving, what is that going to do to the amount of sticking together that can happen when they collide? Right? So if they're moving slower, they are less likely to bounce apart. They're more likely to stick together and even condense to form a liquid. So at lower temperatures, real gases deviate more than they would at higher temperatures. And again, why would that be? So think about what we just said, rewind if you need to, and think about your why there. Okay, so let's talk about actually using this in an equation. So even at room temperature, it says, even at room temperature and pressure, we do see slight deviations from PV equals nRT. And van der Waals equation, which you'll see there in your notes, looks complicated, but really all we're doing is we're replacing the P and the V in PV equals nRT. We can see the nRT is still there. We're just replacing them with a little accounting for the attractiveness of particles, the IMFs, and also the volume of the particles have. And the only symbol that you've never seen before, at least with gas laws, is this lowercase a, and that is a constant that you can see listed right here. It's down below in your notes handout. But that constant there, you can see it is different for different gases, and it does depend on the type of intermolecular force and the size of the particles. So you can see helium has a really low value for A, so does hydrogen. That's because those have really small intermolecular forces, whereas ethanol, which has hydrogen bonding, has a really large value for A. So when ethanol molecules interact, they tend to attract each other a bit more. Now the B value corresponds to the volumes of the particles, and it doesn't equal the volumes of the particles, it just corresponds to them. So particles that tend to take up more space will have a larger volume for B. And it's a bit more complicated than that, which is why you don't see like a direct relationship between molar mass and B values, but that's the gist of it. Okay, so let's see if we can solve a problem. It says, what pressure do we expect SO2 to exert if we have 0.85 moles of it and its volume is 19.5 liters at 25 degrees Celsius? So normally we would just set this up to solve for P. You know, if we were using PV equals nRT, it would just be P equals nRT over V. Well, we're going to actually rearrange van der Waals equation to get P by itself, and that's going to be a little bit more complicated, right? So we're still trying to solve for pressure, but it's going to be a little bit different. And so to do that, think about what you would have to do mathematically to get P by itself here, right? We're going to have to subtract the AN squared over V squared, all right? And we're going to have to divide both sides by V minus NB. We have to do both of those things to get P by itself. So we should end up with a new equation that looks like this. Pressure equals nRT over V minus NB minus AN squared over V squared, okay? And so from this point, after we've rearranged our equation, it just becomes a matter of plugging the numbers in, okay? And so our number of moles is 0.85. Our R value, we have to use 0.0821 because if you'll notice our A is in atmospheres, or has atmospheres in it, I should say. So we have to use 0.0821 for R. Temperature, of course, we want it to be in Kelvin, so 298 kelvins. Volume is just the volume given to us, 19.5 liters. N is, again, 0.85 moles, and B will be the number from the chart. So for SO2, it's going to be 0.05679 minus, and then over here we have this fraction, A is 6.865. Don't forget your units. N squared now, so that's going to be 0.85 squared. And then that's going to be over volume squared, so 19.5 liters squared. Now that's a lot, but it's just plugging it into the calculator. And when you do that, it should look like this, okay? And it gives us a pressure of about 1.05 atmospheres, all right? So I didn't show my work for this, but if I were to go ahead and plug in and just solve for it without accounting for, van der Waals equation, and if I had solved it, in other words, like an ideal gas, using P equals nRT over V, I would have gotten about 1.07, so a little bit higher number of atmospheres of pressure. But again, because that SO2 molecule has some volume itself, and also because it attracts other SO2 molecules, that's going to bring that overall pressure down from about 1.07, which is what we would have predicted using the ideal gas law, down to a more realistic 1.05. So that's how we use van der Waals equation. And you will only have to use this form of it. So you'll only have to use the one that is rearranged to solve for pressure. Okay, and then this last one I'm not going to do. I'd like you to try it. So it says use van der Waals equation to determine its exact pressure under these conditions, meaning the pressure of the water vapor. So I'm giving you the moles, the volume, the temperature. So calculate the pressure of the gas under both real and ideal. So ideal just means P equals nRT over V. Real would be what we just did, but make sure you're using the A and B values for water vapor. The percent deviation, you can try to figure that on your own. Otherwise, we will talk about that in class. But do try to calculate the ideal and real pressures of water vapor under those conditions.